Hello, everyone. Thank you for joining us today. Our project is focused on optimizing emergency response, predicting and mitigating serious accident injuries. Over the next few minutes, we'll be talking about how we created a predictive model to help emergency services respond better to traffic accidents. First, let me introduce our team. My name is Amayrani Balbuena, and I'm here with Jun Clemente and Matt Ammirati. We work together as data scientists to create a model that can predict how serious an accident might be, helping emergency teams respond more effectively. Let's start with an overview of the problem we're addressing. We started this project because traffic accidents are becoming more common, which puts a lot of pressure on emergency services. They often struggle to respond quickly because it's hard to know where resources are the most needed. The main problem is that traffic accidents are unpredictable, making it difficult for emergency teams to get to the scene quickly. These delays can lead to more serious injuries and, in the worst cases, fatalities that could have been prevented. Our project aims to fix this by improving how resources are allocated during emergencies, helping to save lives and reduce the severities of injuries. Given these challenges, our goal was to create a model that can accurately predict how serious a traffic accident might be. This model is not just about predicting outcomes, it's about helping emergency services make faster, more informed decisions. By using our model, we aim to optimize how resources are allocated, which can speed up response times and improve outcomes for people involved in accidents. In simple terms, our model seeks to save lives by making emergency responses more efficient. To build our model, we started by analyzing a data set of road traffic accidents from Kaggle, covering the years 2017 to 2020. This data set includes over 8,000 records, giving us a strong foundation for our analysis. Our first step was to clean the data, which involved filling in missing values and confirming that there were no significant outliers. In the next step, we focused on selecting the most important features, which we will discuss on the following slide.
For the feature selection process, we worked with a dataset of 8,210 records, from which 9 key features were selected out of 33 variables. These features were identified based on their strong relevance to the target variable, accident severity, which is categorized into 3 levels: serious injury, slight injury, and fatal injury. The goal was to ensure that the chosen features provide the most predictive power for understanding and predicting the severity of accidents. The chi-square test was used to determine which features had significant correlation with a target variable. P-values less than 0.05 are considered statistically significant. This example shows 3 variables that were chosen due to their p-value. Vehicle movement was not selected due to its p-value being greater than 0.05. On the right is the Kramer's V correlation matrix, showing the strength of relationships between categorical variables. Although our chi-square test showed strong correlation, the Kramer's V statistic shows that they are not as strongly associated. We tested several algorithms, including decision tree, k-nearest neighbors, logistic regression, naive Bayes, neural network, and random forest to identify the best model for predicting accident severity. For model training and evaluation, we split the data into 70% for training and 30% for testing. We used five-fold cross-validation to ensure robustness. Due to the imbalance in the target variable, we used random oversampler to balance the classes. Our target success criteria were set at 85% for accuracy and 90% for precision. We compared each model based on the following metrics. The random forest model stands out, achieving the highest accuracy at 96% and surpassing our target precision with 92%. Although it wasn't part of the success criteria, it also excels in specificity and recall, which shows a strong balance between detecting true positives and minimizing false positives. K-nearest neighbors also performed well, but its precision was not as good as the random forest model. Overall, the random forest model meets and exceeds our target criteria, making it the best choice for predicting accident severity. Another metric used to compare the models is the AUC ROC curve. The receiver operating characteristic curves for the 6 models we tested are presented here along with a baseline model. The ROC curve shows the trade-off between the true positive rate or sensitivity and the false positive rate for each model. The area under the curve score is a key metric here. It indicates the overall ability of the model to distinguish between classes. The random forest model, shown in red, has an AUC of 0.98. It outperforms all other models, closely followed by the decision tree at 0.90 and k nearest neighbors at 0.86. These curves confirm that the random forest model is the most effective in predicting accident severity, as it consistently achieves a high true positive rate with a low false positive rate.
Out of the 6 different models that we analyzed, the random forest model performed the best. The random forest model achieved an impressive accuracy of 96%, meaning it correctly classified the majority of the instances, making it a highly reliable model for our predictive needs. With a precision of 92%, the model is effective at minimizing false positives, ensuring that when it predicts a positive class, it's correct most of the time. These metrics suggest that the random forest model is highly effective for our application, whether it's optimizing resource allocation in response scenarios or identifying cases with higher risk that require more immediate attention. There was really only one challenge with our data set, and that was that the target variable had 80% of the accident severity as slight injury, while the remaining 20% was severe injury. This caused an issue with bias in the model performance. With such a disproportionate distribution, our model is at risk of being biased towards predicting slight injury. This means it may not perform as well in identifying severe injuries. The model's ability to detect and respond to severe cases might be compromised, potentially affecting how quickly and effectively we can address critical incidents. There are many different ways to address this. Oversampling is the most common technique used here. There were limitations associated with this project, one being neural network performance. The neural network struggled to accurately classify severe injury cases, which is critical in applications such as emergency response. The model also exhibited a low recall rate for serious injuries, indicating that it failed to identify a significant portion of these critical cases. Another limitation is the feature complexity. The model currently uses a large number of features, which might not all contribute meaningfully to its performance. There's an opportunity to simplify the model by identifying and removing redundant or irrelevant features, which could improve efficiency without sacrificing accuracy. Another limitation was making the model more generally applicable. The model was trained on data from a specific time period, which may limit its ability to generalize to new or unseen data. To ensure the model's robustness, additional validation on more diverse data sets from different time periods or regions may be necessary. Let's wrap up with our key findings and discuss where we go from here. Our primary achievement was the performance of the random forest model, which stood out with an impressive 96% accuracy and 92% precision. This result highlights the model's robustness and its potential to significantly improve how we respond to accidents. By accurately predicting the severity of accidents, we can optimize emergency response efforts, ensuring that resources are allocated more effectively and lives are saved. Looking forward, there are several areas where we can refine and expand on our work. First, we plan to simplify the model by reducing the number of features. Techniques like PCA can help us identify and retain the most critical variables, streamlining our model while maintaining accuracy. Next, we'll explore new methods, including different sampling strategies and alternative machine learning algorithms, to see if we can push our model's performance even further. Another critical step is to validate our model on more diverse data sets. While our current model performs well, we need to ensure it generalizes effectively in the real world, especially with different types of data. Finally, we will continue to focus on proper feature selection techniques, ensuring that our model remains both accurate and efficient by using the most relevant variables. These steps will not only enhance our model's performance, but also increase its real-world applicability, making it a valuable tool for improving emergency response systems. With this project, we have identified a model that could significantly impact emergency response efficiency. By leveraging its high accuracy in predicting accident severity, the model can facilitate faster and more effective responses and ensure critical incidents are prioritized. Key impacts are enhanced emergency response. The model allows for swift and precise responses by predicting accident severity accurately, ensuring those in urgent need receive timely assistance. Optimized resource allocation. It helps in prioritizing resources for the most critical incidents, improving overall resource distribution and utilization. Potential practical applications include emergency services. The model could aid in determining which emergency calls necessitate the fastest response, and policy development. The insights derived from the model could guide the creation of data-driven public safety strategies and improve resource management.